Hello, and welcome to today's Oil and Gas Journal webcast, Driving Innovation in the Oil and Gas Industries Through the Use of Materials Modeling and Simulation, sponsored by Dassault Systèmes BioVia. I am J.B. Avance, Oil and Gas Journal's equipment editor and your moderator. Thank you so much for joining us. Today's webcast will be presented by Nick Reynolds with Dassault Systèmes BioVia. Before we begin, just a couple of webcast housekeeping items. This presentation is live and interactive, so you may ask questions at any time by clicking in the Ask a Question box in the presentation window, then clicking the Submit button. If you are running pop-up blocking software, you will need to disable it to view this webcast. In addition, it is recommended you close down all other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from the home page at www.ogj.com. If you would like to download a PDF copy of today's slide presentation, you may do so by clicking on the Event Resources tab on your webcast console. And now allow me to introduce Nick Reynolds, Principal Application Scientist with Dassault Systèmes BioVia. Mr. Reynolds received his Ph.D. in Polymer Science and Engineering from the University of Massachusetts Amherst. He then worked as a postdoctoral research associate at the Max Planck Institute for Polymer Research in Mainz, Germany. Nick has been a BioVia employee since 1992. He provides support in the use of materials modeling and simulation technology and laboratory informatics solutions for companies in the oil and gas, chemicals, polymers, consumer packaged goods, and pharmaceutical industries. And now it's my pleasure to introduce Dr. Nick Reynolds.
Okay, thank you, JB. Yes, today we'd like to talk about areas in which materials modeling and simulation tools can be used to drive innovation, particularly in the oil and gas industries. I'm from BioVia, which is a brand of Dassault Systèmes, and BioVia is really a brand of Dassault which deals with science and working with companies that use science to drive innovation. And so really working with customers that are focusing on science to help drive their R&D processes. So BioVia provides a broad range of software tools. In the upper left-hand corner is the Unified Laboratory Management. This is really around the areas of laboratory operations, how work is done in the laboratory. That could be from the design and execution of experiments, requesting tests to be done, and handling all of the data and easing collaboration in a laboratory. Today we're going to be focusing really on the bottom half of this graph, really the collaborative science area, and in this case using computational material science to help product development and to drive innovation. So when we talk about diverse scientific processes, so our software tools can be applied to understand chemistry, and we'll go through some examples around catalysis. So being able to understand chemistry, biology, material science, formulations. That could be around data modeling of formulations, building predictive models to relate, say, the amounts of components to formulation performance, dealing with numerical data, chemical reactions, and we'll go through some examples of that, and the ability to predict properties of materials like solubility, adhesion, tensile strength, and so forth. So in terms of why organizations use computational material science, really the goal is to use virtual screening, testing on the computer prior to the laboratory to help drive the experimental work. In many cases, modeling can provide insights that are not directly available from experiment. They're often used to interpret and explain what is observed experimentally. And there are a number of studies talking about being able to reduce the number of experiments, or basically guide experimentation to work with those candidates that would be most likely. And there are examples of where the return on investment can be quite significant in the use of simulation, again, to help drive experimentation, to avoid dead ends, and really to gain a fundamental understanding of the materials that one is working with. So we talk about multi-scale materials modeling. So at the most fundamental level, using quantum mechanics, and we'll go through some examples today of being able to study chemical reactions. So these are often used in the design of catalysts, in chemical reaction engineering, understanding a variety of processes taking place in chemical reactions, so activation barriers, understanding transition states. The next level up, what's termed molecular mechanics, these are often applied to predict properties like the solubility parameter of a material, or predicting mechanical behavior, thermal properties, coefficient of thermal expansion, for example, or glass transition temperature of polymers. More coarse grain, or here termed mesoscale simulation, allows one to look at mixtures. If we blend polymers or we blend different surfactants together, what sort of structure do they form? How do they phase separate? If we have a mixture, is that actually a stable mixture, or will it phase separate? And then these models can then be used as input then for bulk engineering scale simulation. So the goal here is to be able to connect the different length scales that answer different questions and treat different phenomena. So Biovia provides a product called Material Studio, which is a comprehensive platform for materials modeling. So it has tools to be able to build structures, so build catalysts, polymers, crystals, amorphous materials, to visualize them, and to use advanced simulation tools to be able to predict properties. And we'll go through some examples around catalysis, predicting solubility, predicting properties like viscosity, mechanical properties. So it provides a broad range of different types of simulation tools that are used to directly predict the properties of materials. And we're going to go through some examples that are relevant in oil and gas. So one of these areas is the catalyst design cycle. And so when we talk about the development of catalysts, so much work goes on in the early stages of discovery, of identifying which materials are going to be successful catalysts, both for homogeneous and heterogeneous catalysis. And this process can take a number of years, and really simulation can provide value in being able to shorten the early discovery stages of that. And in this case, information and knowledge flow within each stage is very important. So there are a number of examples of where these tools have been applied. So here, based on a paper studying a particular reaction, so a hydrogenation of acetylene to ethylene. So in this case, a platinum gold co-catalyst. And the goal here is trying to find, a cheaper, less toxic, non-precious metal to be a catalyst. So simulation work was carried out to be able to predict the heat of absorption of molecules on the surface of the catalyst. And in this case, a number of different catalysts were virtually screened on the computer. In this case, a nickel zinc co-catalyst was found to be quite effective. So there are a number of studies of where these tools have been used to be able to predict reaction energies, or in this case, heat of absorption. These approaches are often used to understand the mechanism of chemical reactions. So hydrodesulfurization catalysts are very important in refining, but the mechanism of how these work was elusive and was not really known, was the subject of a number of research studies over the years. And in this case, simulation was carried out to be able to understand the exact mechanism by which these particular catalysts operate. So with that information, then catalysts can be more easily designed with a fundamental understanding of the chemical mechanisms that are taking place. These approaches can be applied to heterogeneous or homogeneous catalysts. So this was a study in looking at NO absorbing onto a copper 111 surface, being able to study as you change the chemical nature of the surface, how does that control the binding of molecules? In this case, of being able to look at ethylene epoxidation catalysts and the effect of chlorine and how that affects the surface chemistry. And so there are a number of examples of where these tools have been applied to be able to study catalysis and understand catalytic reactions. So one particular study that was done together with researchers at the Stevens Institute of Technology, also with Utrecht University and at Biovia. So this was studying a series of Fischer-Tropsch catalysts. In this case, they're using infrared spectroscopy to characterize the materials and understand what's going on, and including then quantum mechanics simulations, so density functional theory calculations to do this. So there's been a lot of work that's been done in understanding Fischer-Tropsch reactions, so the syngas to fuels. This is talking about the number of patents that have been made available over the past years. There's a lot of research work that has been going on in this field. And really the goal of this particular study was understanding cobalt as a catalyst on top of a titanium surface. And in this case, infrared spectroscopy was used to characterize the materials, and then simulation methods were then carried out to be able to understand the chemical mechanisms. So experimentally, it's known that the CO stretching vibration, which is shown in Lars on the right side, that's changing during reaction conditions. So that's one way of being able to characterize how the reaction is taking place. And so there are different features. This split CO double peak, which is seen, it's known to be related to carbon monoxide on top of a cobalt. It's seen for cobalt supported by a number of different materials. So these materials have been fairly well characterized to understand the surface chemistry, the size, particle size, and what's going on in terms of reaction going on, and following the infrared spectra as that's changing for cobalt on top of the titanium support. So the, the vibrational spectra is followed as a function of temperature. These peaks are seen to either increase or decrease, and so that's able to follow chemically what's going on. And where simulation is very valuable is to be able to interpret the spectra, to be able to assign those peaks to specific structures and understand what's going on. So density functional theory calculations were carried out with Material Studio, and here we're looking at a number of different particular structures of cobalt, so different surface chemistries. Here the 102 or 001 surface. If you remove different atoms on top of that, or at the bottom where we have the cobalt 001 surface, either at a sixth, a third, or a half a monolayer coverage of oxygen on top of that. So these models could be then simulated to be able to predict, okay, which has the lowest energy to understand, okay, what's going on in this particular reaction. So these materials were well characterized through a variety of different types of spectroscopic methods, and then temperature program reduction was carried out to follow the reaction that's taking place as you're heating the materials. And so the formation of this cobalt oxide form, which is known and can be observed from XPS spectra. So models were constructed and simulations were carried out to look at the relative energies of these structures and being able to understand here a cobalt layer on top of a cobalt oxide structure, and then simulating the carbon, the CO binding onto that surface, and then predicting the vibrational spectra. And so this approach could be then used to determine what is the lowest energy structure of this cobalt oxide phase that's present on the surface, and then how the CO structure then bonds onto that. So by carrying out this work, building these different models, one can simulate the vibrational spectra to then be able to study the formation of the CO bonding onto these different types of structures, both the pure cobalt as well as the cobalt oxide phase. So the spectra are known to change as a function of time and in temperature as the reaction is taking place, and again, simulations allow one to directly predict what those vibrational frequencies would be. And then from this, by evaluating the intensity of the IR peaks, this allowed one to determine what the approximate size of these particles is and the ratio of cobalt and cobalt oxide. So in terms of these Fischer-Tropsch reactions, one could look at a number of different reaction mechanisms. So how this is taking place, a direct carbide insertion occurring on the cobalt surface, CO insertion, or this oxygenation reaction. And then carrying this out to be able to study the reaction processes and calculate the energy of reaction. So this is looking at the CO then bonding directly onto the cobalt surface or the cobalt oxide surface. So the reaction mechanism is fairly similar, however the energy of reaction is much lower on the cobalt oxide surface. So the approach this is used to be able to study these types of materials and to help interpret the spectra. So in this particular study, IR spectroscopy was carried out to study the reaction taking place as a function of time and temperature. The energies are quite different, whether this is occurring on pure cobalt or cobalt oxide. And so the reaction energies could be determined. The mechanism by which the reaction takes place can also be studied, as well as understanding and being able to interpret the spectra. So a number of approaches are used in the development of catalysts. There are also quantitative structure property relation methods. So this is some work that was done at Arkema, where they're using different features of the chemical structure to be able to build a statistical model which links chemical features. That could be the size, the shape, the hydrophobicity, the distribution of electrons, dipole moment. So a large number of structural properties can be quickly calculated and then correlated with experimental catalytic activity. And this approach, this quantitative structure activity relationship approach, where you're developing a statistical model to link chemically relevant parameters, things that you can quickly calculate, to the experimental catalyst activity. That approach can then be used to screen a wide variety of different types of catalysts and then predict what their performance will be. Again, to help drive the development of what things should be tested next. If we change, say, the ligands on a particular metal center, is that going to increase or decrease the reactivity of it? So simulations can be carried out to look at other types of materials. There's a lot of work that's been done in zeolites, other microporous materials, for separations. So gas separation, understanding how these molecules will bind onto the surface. So one can calculate properties like sorption isotherms, understand if we have a zeolite structure and we're pumping gases into that, what is the binding energy, how do they bind, where do they bind, and if we're putting different gases in, how are they going to sorb into that material. So these have been widely used in the development of catalysts and for separation. So this approach of being able to study organics, in this case, predicting water adsorption isotherms in a silicate and the illuminated zeolite. So one could use this to be able to predict as a function of temperature and pressure how much water is going to be stayed in that structure. So these sorption simulations have been used for a number of years to be able to study gas separation. Also features such as shape selectivity. We may have similar types of molecules that may differ by a very slight chemical feature, but that changes their shape and therefore the barrier for mobility of that molecule through the zeolite structure. And so there are a number of studies that have been carried out being able to understand how these molecules bind onto the surface and how certain zeolites can be used to separate compounds based on their shape. So one challenge in the petrochemical industry is problems like asphaltene precipitation, so clogging pipes. And so there's a lot of work that's been done over the years of understanding, okay, the nature of these asphaltene precipitates. And modeling and simulation can also be applied to understand this problem. So one of the challenges to modeling that, okay, is what is the structure? You know, asphaltenes are a class of different types of aromatic materials. There's not one, pure type of structure. And how can one model the precipitation process? So simulations can be used to help in this area. There's a large amount of experimental work that's been done to characterize these materials, to understand chemically what they are consisting of. And simulations can add information to that. So by building models of different structures, one can predict properties like the infrared frequency or UV absorbance spectroscopy. So one can directly predict these types of spectra based on a molecular model. So in terms of vibrational spectra, one can build simple models, optimize them, and then, as shown here, directly calculate the infrared or Raman frequencies and intensities. And so from this, one can then be able to assign the different vibrational modes to what is seen in each of the peaks in the spectra. And that's a very common application of these tools to help interpret the spectra and to understand chemically which functional groups represent that. So this approach here, looking at specific hydrogen, so carbon-hydrogen stretching frequencies or outer plane motions, to help, again, to understand the nature of the structure and compare the simulated spectra to experimental to be able to validate that we have a reasonable model of what we think that structure would be. So these methods have been applied to look at both infrared spectra, Raman spectra, UV visible spectra, and then to understand, okay, the precipitation process. So, okay, the asphaltene molecules, you have these aromatic rings that begin to stack, these little nano aggregates, and they form clusters, and those clusters eventually grow into networks. So we're trying to understand, okay, the basic process that's occurring in the precipitation. So different ways of doing this. So one can study the energy of forming dimers to understand the thermodynamics of that, for instance. So one can build models to calculate what is the attraction energy, what is the binding energy as you bring these molecules together, or how much energy is required to then separate them. And so that can be done using methods like molecular dynamics simulations, where we build a model to represent, say, this liquid state, and then study the interaction between them. These approaches can also be applied to calculate free energy, or what's known as the potential of mean force. So how much energy is required to, say, pull a molecule away, out of that dimer, which is what's going to happen as a solvent would come in to begin to break up the precipitate. So simulations can be carried out to do this type of work. And this slide here is showing these potential of mean force curves. And the idea is that the bottom of the curve represents the minimum in energy. So that's when you have a very stable aggregate of these molecules bound together. And then the maximum in the peak is really this transition state where we begin to pull the molecules apart. And that's the point where a solvent would be intercalating in between the molecules in the aggregate. So one can study this process and understanding what that binding energy is. So using molecular dynamics simulations, where we take this model of the liquid state, we heat it, and we look at the dynamics of how these molecules move, the energy of that structure. And we were interested in, okay, do these molecules stay close together over time, or do they begin to drift apart? And so this is a plot showing the distance between these molecules in different solutions, different solvent states. So in the case of a heptane solvent, the dimer separation doesn't change. Basically, those two molecules, they want to stay near each other when they're dissolved in heptane, which indicates that particular asphaltene is not soluble in heptane. However, in toluene, that's the upper plot, we're showing the distance between these molecules changes as a function of time. So in this case, these molecules are able to be separated by toluene. These can be used to be able to understand, as we change the nature of the solvent, how does that affect the interaction of these molecules and ultimately the breaking up of that dimer. So these approaches have been applied to look at other types of properties like viscosity, for instance. So this is a study that was done at Lubrizol where they have experimental data on different lubricants where they're looking at traction coefficient. And so they want to understand, as they change the chemical structure of this particular lubricant molecule, how will that affect the traction coefficient? So they had a lot of experimental data, and they had built chemical models of each of these structures and then calculated descriptors. So properties like the dipole moment, the size, the shape of the molecule. There are different ways of quantifying the degree of branching, the electrostatic behavior, and then developing a statistical model to correlate these molecular features with the experimental traction coefficients. So by taking that experimental data, they then train this model, this quantitative structure activity relationship model, which they could then virtually screen new structures. So once they have this model built, then plug in a variety of new molecules into it and then predict what the traction coefficient would be. So this is a way of being able to use virtual high throughput screening to screen a wide variety of different types of structures and identify those which look to be promising, the things that actually should be tested in the laboratory. So these approaches are really used to help organize experimental data and understand what is the relationship between chemical features, and in this case the experimental traction coefficient, then build a predictive model to help guide in the selection of the next materials to be able to test. So this quantitative structure activity approach is a very common method that's applied in a number of different industries, again, to be able to link chemical structure with some experimental observable. And then again, from that, being able to screen new structures, perhaps untested or even unsynthesized molecules, to identify the things that look most promising to then test in the laboratory. So these approaches of quantitative structure activity or quantitative structure property relationships have been applied to a wide variety of different types of studies. For instance, viscosity prediction. So by taking experimental data for a number of different hydrocarbons and being able to use this QSPR method to link chemical structure features, again, like dipole moment, shape, distribution of electrons, degree of branching, to the experimental viscosity, one could build a predictive model and then use that to predict the viscosity of new structures. And so these type of methods have been applied to predict a wide variety of properties of compounds, including viscosity. Another application in the petrochemical field is some work that was done at Halliburton. So they're developing a model, basically a propant molecule modeling. So they developed a new product basically for keeping the clay layers open as oil was being extracted from the field. And so they wanted to understand basically a particular polymer additive, how it would bind onto the clay layers. And so they built models to represent the surface and how different polymer structures would bind onto that, again, to help keep these fractures open. And they developed a product, sand wedge, through the use of simulation to help guide the testing of what molecules to look at. So they used modeling to understand, okay, as they change copolymer composition, was that going to affect how that molecule would bind onto that surface? So using this virtual screening or in silico screening, that helped them determine what molecule would be best for that application and helped in the development of the sand wedge product. So I'll stop at this point and ask if there are specific questions, and I would be happy to answer any of those.
All right, Nick, thank you very much. There are a number of questions here, and so we will start with the first is, how does this technology play into the bulk and multi-scale world of refinery operations and maintenance?
So in terms of multi-scale simulation, people have applied this to predict and as they mix materials together, how they would phase separate, to look at the stability of mixtures. There's also a lot of work on the chemical engineering side, using simulation to calculate reaction barriers and rate constants. So one can calculate chemical rate constants, and then those can be fed into chemical engineering simulation to understand, as a function of temperature and time, the amount of reactant, as reactants are decreasing and the products are increasing in quantity. One can calculate those types of properties. I think the multi-scale modeling, that's often on the structural side, where people are calculating either properties that would feed into engineering simulation, and again for chemical reactions, being able to directly predict reaction energies, activation barriers, and rate constants that can then be used in chemical engineering simulation. And that capability is within the Material Studio product.
Okay. Our next question, how do companies implement a modeling program?
So often it's applied by someone who perhaps is in an R&D that's providing service. They might be providing modeling services to different research teams for specific projects. I think a successful modeling program, it really depends on determining what are the challenges, what are the problems that you're facing, and understand, okay, is chemistry related, that one can apply simulation methods to help guide that. I think the success of these methods is it's really dependent that the user of the software is working very closely with the experimentalists to be able to validate the models, make sure they're building structures that are realistic and represent the chemistry of what's going on. So the key, I think, is that it needs to be well integrated in R&D directly.
All right, and also with regard to modeling, what sort of training is needed to effectively use these modeling tools?
So there I'd say a basic understanding of the chemistry that you're working on. Many of the people who use our software, they're not necessarily experts in computational chemistry and computational material science, but they understand the chemistry of the materials they're working with, and so they can be trained to do that. So a lot of our time is spent working with customers to help train them in the application of the model. So how do I build this type of structure? What are the ways to automate that through scripting or through automated protocols that I want to, say, repeat the same type of simulation but on a number of different structures and then predict the results. So I think basically working with customers and training them effectively to make use of the software is really key for success.
Okay. The next is, what sort of computer hardware is needed to use these tools?
So the cost of hardware has decreased significantly in the past few years. I'd say for these type of applications, it's similar to other engineering simulations, so people doing computational fluid dynamics or finite element analysis. That's very common, the same type of computer hardware. So Material Studio is a Windows-based product. It's a client-server application. So you're running the graphical client at your desktop, and the server could be your desktop machine, or it could be a server, a remote server, which could be Windows or Linux. So there's really no specific special hardware that's needed. It's the same type of computer hardware that would be used for other engineering simulations.
All right. With regard to simulation, it says the next question is, will simulation replace or augment experimentation?
Well, it's going to augment. The idea is that it helps to guide experiment. I mean, if you have a certain capacity to do experiments, you're going to continue that. But the idea is that modeling helps to guide that. And many of the companies we work with, they're asking for more virtual experimentation, so that they can find the best candidates more quickly. Fail early and then identify the better candidates. So, not that it's going to necessarily decrease the amount of experiments you're using, but it's going to help guide those experiments so that you find the best result more quickly.
Okay. We have a question specific to slide number 25. How do you calculate the delta H of the two reactions?
Okay. So one can calculate the delta H by comparing the energy of the final state and the initial state. So you build models to represent your reactants and your products, and then the difference in energy is the energy of reaction. Now, if you want the activation barrier, how much energy you have to put in for that reaction to occur, then that's another type of simulation. And there are automated tools in Material Studio to guide in that, to help identify the transition state and therefore the activation barrier. And with that, then one can also then calculate directly the rate constant. But the energy of reaction comes from comparing the energies of the reactants and products.
Okay. Our next question is how to incorporate auxiliary natural physicochemical changes occurring in actual condition but not quantified for laboratory simulation.
So that's a broad topic. I probably need more specifics. I think that's an area where things like quantitative structure-property relations are often applied. It could be you're trying to identify if you change the chemical structure, does that lead to either better or poorer performance? And you may not be able to simulate the entire process that's going through because it's very complicated, but that's where quantitative structure-property relationship methods are often very useful because you're just identifying what is the relationship between chemical structure and ultimate properties.
Okay. The next question, can you cite a work describing the use of calculations for evaluating the surfactant self-assembly properties?
Yes, and there's a lot of work that has been done to study self-assembly of surfactants, both in areas like consumer packaged goods, for soaps, but also for enhanced oil recovery. So there are examples of where these tools have been applied. So coarse-grained mesoscale simulations, where you don't have every atom represented. You have, say, a bead or particle that represents, say, the head group of a surfactant, or a number of these beads might represent, say, the hydrophobic tail. But these approaches have been used to look at phase separation, to understand interfacial tension, critical micelle concentration. So yes, definitely these approaches can be used to study self-assembly of surfactants, and there's a lot of studies in which they've been, that work has been done, and this type of study can be done in Material Studio.
Okay. How accurate can reaction mechanism simulations be without tuning them with lab data?
I guess that depends on the reaction. I think, in many cases people have applied this to a reaction they understand well to validate the method to see, okay, how close am I getting to, a energy of heat of formation or an activation barrier. And then once they validated that, then they know they can apply it to systems that they haven't studied before. I think having some information on the reaction itself is very valuable, but there are many cases where people don't have that information, and they're trying to understand, okay, if I change chemical structure, how does that affect the mechanism, and how does that affect the energetics? So I'd say one, if data is available, it's great, especially to help validate the approach. And what level of theory do you need to use to carry out these simulations? It's always a balance of, you want sufficient accuracy to answer your problem, but you want it at a quick simulation time so you can get the results more quickly. So I think there are cases where there wasn't experimental data and people were still able to apply these methods to gain insight in how these reactions occur.
All right. And this question, how do you see this tech fitting into upstream exploration in the next 1 to 2 years? In terms of upstream exploration, I'd say, most of the work, of course, has been more downstream in the application of these simulation tools. But certainly understanding the interaction of molecules, say with, you're looking at clay surfaces, for instance, and understanding as you apply pressure what the interaction is or how molecules are flowing and predicting properties like viscosity. There are applications more upstream where it can be applied. So I think in understanding surface interaction is probably the area where it would be best applied. Okay. Well, I want to thank you for the questions and obviously, Nick, for your answers, but any closing thoughts as we begin to wrap up?
Yes, I'd say, these tools have been developed, over a number of years and are being applied more directly, in the oil and gas field. I think the time is ripe to be able to apply these tools, especially since there's better accuracy that can be applied to looking at chemical reactions. And now that the link with chemical reaction simulation is carried out directly, so I think there's a lot that can be done in linking, chemistry at a more fundamental level to be able to apply that to help chemical engineers.
All right. Well, I thank you on behalf of Oil and Gas Journal and Penwell Corporation. I thank you, Dr. Reynolds, for this outstanding presentation, and of course our sponsor, Dassault Systems Biovia. This presentation will be archived within 24 hours and can be reached from the home page at ogj.com. A reminder email message will be sent to all registrants, complete with a direct link to the archive. And we thank you for joining us today and look forward to serving you with future webcasts.